It's crazy, isn't it? Like, how fast AI is changing.
It really is.
I mean, just a couple of years ago, it was all about these massive single models.
Right.
But now we're seeing these really cool systems emerging where it's not just one big model, but a bunch of different LLMs, large language models working together,
Yeah.
almost like an AI orchestra.
Exactly. A whole set of specialized tools orchestrated together.
Yeah, and I think what's really fascinating right now is that the way these like intricate systems get optimized, it's still very much a manual process.
Yeah, very human-driven.
It relies so much on intuition, trial and error, a ton of experiments.
Yeah, and it's almost like a bottleneck to faster progress.
It really is. It kind of takes me back to the early days of neural networks, right?
Right.
You had all these cool designs, but training them,
Yeah.
it felt like guesswork, like we didn't really have a great handle on it.
Yeah.
Then came backpropagation
Right.
and automatic differentiation. And that was like,
The
oh,
big aha moment.
like here's a much more automated way to actually optimize these networks.
Yeah, and it really changed the field.
I mean, fundamentally changed the field,
That's
and that's kind of where TextGrad comes in.
That's a great comparison. Yeah.
So this is a new framework, and we're going to take a deep dive into this today.
Right.
The goal is to bring that kind of automated optimization, the kind of revolution that we saw with backprop, but bring it to these modern generative AI systems that we're talking about.
Exactly.
And it uses, the core concept is really interesting. It uses feedback from the LLMs themselves
Right.
to guide the improvement process. So we have the research paper here that goes into all the details of this new approach, shows some really promising initial results.
Yeah.
So let's dive in.
All right.
I'm really curious to understand how this all works.
So maybe we can start with the idea of textual gradients.
Okay.
Right. So you mentioned backpropagation and using numerical gradients to
Right.
kind of adjust the internal parameters of a neural network.
Yeah.
Now, when we're dealing with these modern AI systems, especially these generative AI systems, things are a bit more complex.
They are more complex.
We have natural language.
Right.
We have these LLMs that are often black boxes. We don't have access to their inner workings.
Right.
And we also have external tools that are part of the process. So it's not as straightforward to apply those traditional optimization techniques that rely on numerical gradients.
Yeah, totally. Like when you've got steps involved that are like generating text that sounds human-like or like interacting with a search engine as part of the process, it's not easy to figure out how little changes inside the LLM would actually affect the final outcome.
Right.
So how does TextGrad handle this? What's the approach?
So the key idea here is what they call differentiation via text.
Differentiation via text. Okay.
So instead of using numerical gradients, TextGrad leverages the LLMs themselves to give feedback.
Okay.
And this feedback comes in the form of natural language critiques.
Ah, interesting.
And these critiques are what they're calling textual gradients.
Okay.
So it's basically the LLM saying in plain language, hey, here's where things could be improved.
Textual gradients, I love that. It's a really very descriptive term. So it's almost like the LLM it's looking at the work the AI system did, and it's kind of giving suggestions on how to make it better.
Precisely.
Mm.
And what's important here is that this feedback is not aimed at the internal working of the LLMs,
Right.
which are often inaccessible to us anyway.
Right.
Instead, it focuses on how to modify different components of the AI system.
Okay.
Things like the prompts we give to the LLMs or the intermediate outputs, the final outputs, basically anything that can be changed to enhance the overall performance.
Right. So not going into the internals of the LLM, but looking at how everything around it is working together.
Exactly.
And that makes it compatible with, those black box LLM APIs that everybody's using.
Exactly. Yeah.
Okay, so to kind of make this concrete, can we walk through an example?
Sure.
I think the paper mentioned a simple setup, like with 2 LLM calls.
Yeah. So imagine you have an AI system
Okay.
where the first LLM takes a prompt and a question and it produces a prediction.
Oh.
So we can represent this as prediction equals LLM parenthesis prompt plus question.
Okay.
Then a second LLM takes an evaluation instruction
Okay.
and that prediction and gives an assessment, right?
Mm-hmm.
So we have evaluation equals LLM parenthesis evaluation instruction plus prediction.
Okay, so you got the first LLM making a prediction and the second LLM basically evaluating that prediction.
Right.
Got it.
Now, if we want to improve this system using TextGrad, we first get feedback on that prediction
Okay.
based on the evaluation.
Right.
So the second LLM basically tells us how that prediction could have been better given the evaluation.
Okay, so the evaluator LLM is saying, hey, here's what you did well, here's what you could improve.
Exactly.
Right.
And then, using this feedback and knowing how the prediction was generated from the prompt in the question, TextGrad can then obtain feedback on the prompt
Oh,
itself,
wow.
suggesting how it could be adjusted to
Interesting.
lead to a better prediction and, consequently, a better evaluation.
So it's like that evaluation, that critique from the evaluator is flowing backwards
Right,
to
exactly.
inform the earlier stages.
Right.
Okay, cool, cool. So I'm starting to get the mechanism here. So you have this signal, but instead of being numbers, it's like natural language.
Yes.
So how does that feedback actually get used to, like, make changes in the system?
Okay, so this is where the concept of backpropagation and what they call textual gradient descent, or TGD, comes into play.
Okay, TGD. All right, now we're getting technical.
So think of it this way. In traditional backpropagation, the one that we use for training neural networks,
Yeah,
we have this numerical feedback about errors, and it's propagated backwards
right.
through the network's computation graph. And it tells each layer how to adjust its internal connections, right?
Yeah, yeah.
In TextGrad, these textual gradients, these natural language critiques, are similarly propagated back through the computation graph of the AI system.
So even these more complex systems, they still have an analogous computation graph.
Exactly. And to formalize this, they introduce this idea of a textual gradient operator,
Okay.
which is denoted as, get ready for this, LLM.
LLM, there it is.
So this operator is what actually generates that natural language critique
Okay,
based on the desired improvement.
got it.
So it takes the current variable,
Right.
let's say the prediction,
Okay.
the feedback it received,
From the evaluation.
from the subsequent step, the evaluation,
Yeah.
and produces a textual gradient, which is basically a suggestion on how to improve that variable.
Right.
So you can think of it as a function that asks the LLM, hey, based on this critique, how could the previous step have been better?
Right, okay.
Okay.
And then that textual gradient, that's what guides how you actually modify the variable.
Exactly.
Whether it's rewriting the prompt, refining an output, whatever you're trying to change.
Right, and that's the role of textual gradient descent, or TGD.
TGD, got it.
It's analogous to gradient descent,
Right.
which we know from neural networks.
Yeah, yeah.
But instead of using numerical gradients to update parameters, it uses the LLM-provided textual feedback
Right.
to guide the updates of these unstructured variables.
Okay.
The prompts, the intermediate results, whatever we are optimizing.
Interesting.
And the paper actually outlines a general approach for how this TGD step can be implemented.
Okay.
It basically involves prompting an LLM to take the current variable and the criticisms it has received
Right.
and generate a new, hopefully improved, version of that variable.
So you're asking the LLM to do the work of actually making the change
Exactly.
based on its own feedback.
That's on the feedback, yeah.
That's cool. Now, what about the objective function?
Ah, yes.
So in traditional optimization, you have a clearly defined mathematical function you're trying to minimize or maximize.
Right.
But how does that work here?
So this is where TextGrad is actually very powerful and flexible.
Okay.
So the objective function doesn't need to be a differentiable mathematical function.
Okay.
It can be complex,
Right.
non-differentiable, or even a black box evaluation.
Huh.
For example, the paper talks about cases where the objective is determined by another LLM.
Right, right.
That's evaluating the quality of the output.
So it's like almost like a judgment call
Exactly.
by another LLM. Okay.
Or it could be determined by the results of running automated tests on a piece of code.
Right.
Or even by the outcome of a specialized simulation.
Wow.
So because the feedback is in natural language, it can kind of bridge these different forms of evaluation signals.
Right.
So the goal, what we're trying to achieve, can be defined in a very broad range of ways.
Okay, so we've talked about textual gradients, the idea, the concept.
Yes.
We've talked about the mechanics of backpropagation using this textual feedback
Right.
and this flexibility in defining what we want to achieve.
Exactly.
So let's talk about, does this actually work?
Right.
Let's see it in action.
Right.
The paper showcases TextGrad in like a huge variety of applications.
Yeah, a diverse range of tasks.
Which is really cool.
Right.
So let's start with code optimization.
Okay.
They use this leak code hard data set.
Yeah, a very challenging set of programming problems.
Right, which is known for being, pretty tough.
Yes.
So what were they looking at there?
So the goal in code optimization is you take a piece of code that tries to solve a given problem,
Okay.
and you iteratively try to improve it, either in terms of correctness or efficiency.
Right, right. Make it work better, make it run faster.
Exactly. Their refinement objective was to have an LLM assess the code based on its ability to pass a set of automated tests.
Okay, so like unit tests, I guess.
Like unit tests, yeah.
Okay.
So the LLM could then provide feedback on why the code might be failing certain tests
Oh, interesting.
and suggest specific areas for improvement.
So almost like having a code reviewer, but it's an LLM.
Exactly.
Okay, cool.
And they highlight this specific example involving a LeetCode code hard problem
Okay.
about finding subarrays with a median equal to a given value.
Okay, sounds tough.
Yeah. And there was an initial solution generated by GP4o, but it didn't pass all the test cases.
Of course not. It's leak code hard.
But TextGrad was able to identify a specific edge case issue and suggest a correction,
Okay.
which led to a solution that passed all the tests.
Nice.
So very concrete.
Yeah, very concrete. Very cool. And how did it do overall on the leak code hard benchmark?
So quantitatively, they found that GP4o in a zero-shot setting.
Okay, so no special examples given.
No examples, right.
Just the prompt, just the problem.
Achieved a code completion rate of 26%
Okay.
on these difficult problems.
Which is, I mean, not bad for zero shot.
It's not bad, yeah.
These are hard problems.
Right. There's a leading self-refinement technique called reflection,
Okay.
and that achieved 31%.
Okay.
But using TextGrad, also in a zero-shot setting, GP340 reached 36%.
Ooh, okay. That's a pretty good jump.
It is a good jump, and especially considering that reflection was evaluated using a few in-context examples.
Right, right.
And TextGrad didn't use any.
So it's even more impressive, I guess, in that
Yeah.
sense. Okay, that's really cool. So it really seems like it can help these LLMs get better at writing code.
Yeah.
What about the solution optimization for question answering?
Okay, so for solution optimization, the task is to take an initial answer to a question
Okay,
and refine it iteratively
okay.
based on feedback received from an LLM.
Got it.
So the solution refinement objective is basically you prompt an LLM with the original question, the current solution, and an instruction to critically evaluate that solution.
Okay.
And identify any potential errors or areas for improvement.
So again, kind of like a reviewer, but for answers.
Exactly, yeah.
Interesting. And they tested this on, I think, a bunch of different question answering data sets, right?
Right. They use several data sets, including GPQA, which has these PhD-level science questions.
Wow.
They used challenging subsets of MMLU,
Okay.
which covers things like machine learning, college physics,
Oh, wow.
and even multimodal data sets like MathVista and Science QA, which involve visual reasoning.
Oh, so like questions that have pictures or diagrams associated with them.
Exactly.
Right. So
Quite a variety.
yeah, that's a really broad range of question types.
It is.
So what kind of improvements did they see when they used TextGrad?
So they consistently saw performance gains for GPT-4o when combined with TextGrad
Okay.
across all these benchmarks.
Interesting.
For example, on those very challenging MMLU subsets,
Okay.
accuracy in answering machine learning questions improved from 85.7% to 88.4%.
Okay.
And in college physics, it went from 91.2% to 95.1%. On GPQA, performance increased from 51.0% to 55.0%.
Oh,
They also saw improvements on the multimodal tasks, outperforming reflection on both MathVista and Science QI-MG.
okay. So again, consistently better
Right.
than these other methods.
Right. And the paper even gives a cool example of multimodal solution optimization for a visual math problem,
Okay.
where the initial answer made a mistake interpreting a bar chart.
Hmm.
But the LLM feedback identified that error,
Okay.
leading to a corrected answer after TextGrad optimization.
Oh, that's cool. So it's not just about the language, it's understanding the visuals too.
Right. It can reason about the visuals as well.
All right, that's really impressive. Now, the paper also talks about using TextGrad for prompt optimization,
Yeah.
for reasoning LLM. So why is this an important area to look at?
So we know that how we structure a prompt for an LLM can have a big impact on its ability to do these complex reasoning tasks.
Right, yeah. Like even a small change in the wording can completely change how the LLM responds.
Exactly.
Yeah?
So prompt optimization is about finding these effective prompting strategies
Okay.
that unlock better reasoning capabilities in these models.
Okay.
So the typical setup is you have a task, you have a question,
Okay.
you have the LLM's response based on a specific prompt,
Right.
and then you have some evaluation mechanism.
Yeah.
It could be another powerful LLM
Okay.
or a set of known correct answers
Right.
that assesses the quality of the response.
Okay.
And the goal is to find the prompt that maximizes performance on that task.
So you're trying to find the best way to ask the question.
Exactly.
Okay, so TextGrad can be used to do this automatically.
Yeah. Automatically find better prompts.
Okay, so how does that work?
So the researchers looked at enhancing the performance of a more readily accessible model, like GPT 3.5 Turbo,
Okay.
by using feedback provided by a stronger model, such as GPT 4.0.
Hmm.
So they treated the prompt itself, which could include direct instructions and in-context examples, as the variable they wanted to optimize.
Okay.
And they tested this on standard reasoning benchmark from Big Bench Hard,
Okay.
specifically object counting and word sorting tasks,
Got it.
and the GSM 8K dataset, which is about math word problems.
Okay, cool. So again, a range of different types of tasks.
Right.
Yeah. So how did these TextGrad optimized prompts compare to, just using standard prompts or even other prompt optimization methods?
So TextGrad consistently led to improvements in the performance of the initial zero-shot prompts across all three datasets,
Okay.
and it notably outperformed a method called OPRO
Okay.
and achieved performance levels comparable to, or even better than, a state-of-the-art prompt optimization framework called DSPy.
Okay.
So for instance, on that object counting task from Big Bench Hard, TextGrad achieved a 7% improvement over DSPy.
Wow. So it's not just a little bit better, it's significantly better.
Yeah, and the paper also has examples of how the prompts and in-context demonstration was evolved through the TextGrad optimization process.
Oh, interesting.
And often they became more detailed, offered clearer guidance to the LLM.
So it's like the LLMs are teaching us how to talk to them better.
Exactly.
It's really cool. Now, let's move on to something completely different.
Okay.
Optimizing radiotherapy treatment plans.
Yeah, a very different domain.
This is incredibly complex
It is.
and also incredibly important.
Yes, very important.
So this is really fascinating to me.
So radiotherapy treatment planning is a multi-objective optimization problem
Okay.
with two kind of intertwined aspects.
Okay.
The inner aspect is focused on delivering the optimal radiation dose to the tumor
Right?
while minimizing radiation exposure to surrounding healthy organs.
Right. You want to kill the tumor but not damage the rest of the body.
Precisely.
Okay.
So this involves adjusting lots of technical parameters
Right?
based on what they call importance weights.
Okay.
Now, the outer aspect of the problem is figuring out the best settings for these importance weights.
Right. So it's like, how much do you prioritize protecting this organ versus making sure you get enough radiation to the tumor?
Exactly, and finding the right balance.
Yeah, that's a tough problem.
It is, and currently this outer loop optimization is often a manual process. Very time-consuming, relies a lot on the expertise of clinicians.
And I imagine it's probably pretty stressful too, right?
It can be, yeah.
So where does TextGrad fit into all of this?
So TextGrad is used for that outer loop optimization.
Okay.
The researchers treat the importance weights assigned to different regions,
Okay.
the tumor-specific healthy organs as the variables to be optimized,
Right.
and the evaluation comes from an LLM that analyzes the resulting treatment plan
Okay.
in relation to established clinical goals
Right.
and provides feedback on whether the plan is effectively meeting those goals.
Okay.
For example, is there too much radiation exposure to healthy tissue
Right.
or not enough coverage of the tumor?
Right.
And based on this textual feedback, TextGrad adjusts the importance weights in subsequent iterations
Okay.
to try and generate better treatment plans.
Right. And what's really interesting here is you're using the LLM to evaluate the plan based on clinical goals.
Right.
So it's almost like you're combining the medical expertise with the AI's ability to reason and optimize.
Exactly. They actually provided the LLM with examples of clinically approved treatment plans and their corresponding weights,
Oh, interesting.
as in context information to guide its evaluations.
So it's like it's learning from what humans have already done
Exactly.
and then using that to improve. That's really cool. So how did these TextGrad optimized plans compare to, the traditional clinically developed plans?
So the researchers compared TextGrad optimized treatment plans for 5 patients with prostate cancer
Okay.
to clinically approved plans for the same patients.
Okay.
Now, they do emphasize that these are preliminary illustrative results. This is
Right.
not a replacement for full clinical validation.
Yeah, of course. Of course.
But what they found was that the TextGrad optimized plans showed better dose metrics for the targeted tumor area
Okay.
and lower doses to healthy organs compared to the clinically approved plans.
Wow. So even in these early stages, it's already showing some really promising results.
Right.
That's incredible.
And the textual gradients generated by the LLM provided clinically meaningful feedback.
Okay.
For example, suggesting to increase the tumor's importance weight to get better coverage,
Right.
and then adjusting the weights for the bladder and rectum for better protection.
So it's not just saying, hey, this is better. It's giving specific reasons why.
Exactly, providing justification for the changes.
Okay, that's really cool. They even compared TextGrad to, I think, a Bayesian optimization algorithm,
Yes.
which is a more traditional optimization technique.
Right, a standard approach.
And how did it do?
They found that TextGrad not only performed better, but also converged to a good solution much faster.
Wow, that's really impressive. I mean, this has the potential to really, revolutionize radiotherapy treatment planning.
It does, it really does.
Okay, last but not least, the paper also looks at applying TextGrad to optimizing something called compound AI systems.
Yeah.
So what are compound AI systems?
So compound AI systems are basically AI applications that involve the orchestration of multiple different components.
Okay.
And this often includes several LLM modules
Right.
and different specialized tools.
Okay.
So you can think of sophisticated AI agents that need to formulate plans,
Right.
use search engines, interpret code, and generate responses.
Wow.
All within a kind of a sequential workflow.
So it's like a whole team of AIs working together.
Right, very much so.
Okay.
And a specific example they looked at is a system called Chameleon,
Chameleon, okay.
which is a versatile agentic system.
Right.
The original implementation of Chameleon had this static execution flow, meaning it didn't have any inherent mechanism to receive feedback and rectify errors during its operation.
Right. So once it started running, it just kind of went through its steps.
Exactly.
There was no way to course correct.
Right.
Okay, got it.
So TextGrad comes in to introduce that feedback and refinement.
Okay.
So the researchers applied TextGrad to iteratively optimize the output of each module within the Chameleon system.
Okay.
So after the system completes an initial forward pass to generate a response,
Okay.
TextGrad goes back to the output of each module,
Right.
starting from the beginning,
Okay.
and uses the feedback it receives to refine that module's output.
So it's like it's going back and double-checking each step
Exactly.
based on the feedback.
Right, and this introduces a feedback loop into the system's execution,
Right.
which helps to address the limitations of that static flow
Got it.
and prevent errors from accumulating.
Okay, cool.
They showed significant performance improvements on a visual question answering task.
Okay.
That requires using multiple tools in a coordinated way. They also investigated jointly optimizing the instructional prompts, the prompts used to elicit feedback, and the generated solution in multimodal models, and again, they saw substantial gains.
So it's not just optimizing individual LLM calls.
No.
It can handle these much more complex multi-step AI systems.
Exactly.
That's amazing. So the paper concludes by highlighting 3 key principles behind TextGrad.
Right.
It's very broad applicability across a whole range of AI tasks.
Yes.
It's relatively easy to use because it adopts familiar abstractions from frameworks like PyTorch.
Yeah, it's user-friendly.
And the whole framework is open source.
Yes, which is great.
So it's really accessible to everyone.
Right.
And the researchers really emphasize that TextGrad is a big step toward automating the optimization of these increasingly complex AI systems.
It really is.
And moving beyond these manually crafted solutions.
Right.
So to sum up this deep dive, TextGrad is basically harnessing the reasoning capabilities of LLMs
Right.
to provide natural language feedback,
These textual gradients.
which can then guide the optimization of a huge range of different AI systems.
Yeah, from improving code
Yeah,
to answering complex questions.
refining prompts,
To refining prompts.
optimizing medical treatments.
Even complex AI agents.
It's really a remarkably versatile approach
It is.
that automates the improvement process.
And it's very analogous to how backpropagation changed the way we train neural networks.
And that's the really exciting part. It's like if we can leverage the intelligence of AI itself to make these systems better
Right.
across all these different domains, it could really accelerate progress in the field.
Absolutely.
So for anyone who wants to really dive into the technical details and
Right.
explore the different applications,
Right.
the research paper we've been talking about is a fantastic resource.
Yeah, definitely check it out.
So it's almost like it's AI optimizing AI, right?
Yeah.
It's really incredible to think about what the future holds with this kind of technology.
It'll be interesting to see where it goes.
Yeah, absolutely.